discussed that if we send an electromagnetic wave to the atmosphere, it can come back to the earth, it can bend back to the earth and come back to the earth. So now how, if you are sending it in the upward direction, why it should come back to the earth? That part let us try to discuss now. You can see we have two pictures here. Left hand side shows us that we are sending an electromagnetic wave in the upward direction. It is going to the ionosphere. From the ionosphere, it is gradually bending. So gradually it is curving. So you can see there is a curve path in the ionosphere. So from that path, it curves downward towards the earth, then it comes back to the earth, reflects back to the earth. So the path is modified. It was going in the upward direction. It is not getting reflected. If you look at this, you cannot say that it gets reflected, but it is moving towards the earth. Gradually it is bending towards the earth. Now, if we extend these two lines which are from the earth surface to the bottom layer of the ionosphere, on the two lines, which is one is for the incident line, one is for the receiving line, or transmitted line and receiving line. Those lines, let us expand them or extend them in the backward direction. They will meet at a point. That point, the height of that point from the surface of the earth is called the virtual height. And if we are on the surface of the earth, it will appear to us as if this is getting reflected from the point where the height is the virtual height from the earth. So from that point it is getting reflected to earth. It appears like that, although it is physically it is not going up to that point. It is curving in the below portion, lower portion of the atmosphere. To understand why it curves down, how it comes back to the earth, we'll do a certain analysis, or we'll try to understand how it happens. Now, remember that it depends on two things: the frequency of the wave and angle of incidence. Angle of incidence onto the ionosphere. So from the surface of the earth, angle of incidence onto the ionosphere. So at the boundary of the ionosphere, as you go up in the from the surface of the earth, at the boundary of the ionosphere, what is the angle of incidence? So if we choose these two quantities correctly, the frequency and angle of incidence, then this wave will curve back. If these are not chosen correctly, like as I told that omega is greater than omega c, it will pass through the ionosphere, it will not come back. So we have to choose it correctly. Omega has to be less than omega c, or omega has to be at least omega c. If it is omega c, then for vertical incidence it will come back. If it is less than omega c, for other incidents it will come back, other incidence angles. Now, so it will come back to the surface of the earth. Now, what is the advantage of this? This allows us long distance communication. Now, imagine one antenna is on the left side, left extreme end, other antenna is on the right extreme end of the earth surface. Now, these two antennas or these two antenna towers has to be extremely high if we have to have a line of sight propagation or line of sight communication. Otherwise, the portion of the earth comes between these two antennas, so they cannot see each other. There will be no, it is not possible to have a communication link between these two antennas. Now, instead of that, if we are using ionosphere, put these two antennas at these 2 points from where we have incidenting it in the direction of upward direction with an incident angle, and where it hits the earth when it comes back, there put an antenna. So the receiving antenna will receive what is coming back from the ionosphere. So now it is possible, although they are not in line of sight, but it is possible to receive the radiation or receive the wave, transmitted wave. It is possible at a large distance. If it is a small distance, then the antennas will be in line of sight. But if it is in the large distance, because of the curvature of the earth, the antennas will not be in line of sight. So we cannot see, the antennas cannot see each other. Antennas means transmitting antenna and receiving antenna. They will not be able to see each other. So line of sight, LOS, line of sight is called LOS. In short term, it is called LOS, capital L, capital O and capital S. So LOS sight is not possible. So we have to go for non-line of sight propagation, NLOS. Capital N, capital L, capital O, capital S. So NLOS, which is non-line of sight communication, non-line of sight communication or non-line of sight link. So this is one of the methods of non-line of sight link. In this case, it is possible to have a communication over a large distance because of this reflection or because of the bending of the wave from the ionosphere through the ionosphere, provided we have proper frequency and proper angle of incidence. So we can have this distance. Now the distance between these 2 points, the point transmitting point and the receiving point, that distance is called skip distance. If it cannot come back, when it is coming back and hitting the earth, it has to hit at a distance which is more than the skip distance, because this bending cannot be such that it can hit every point between the transmitter and receiver. So the minimum distance between the transmitter and receiver, transmitting antenna and receiving antenna, where the antenna where the wave can be received by the receiving antenna, is called the skip distance. So skip distance is the distance between the transmitting antenna and receiving antenna, and it is the minimum distance between these two where it is going to receive the transmitted wave, where the receiver is going to receive the transmitted wave. So that is what is skip distance. Height, as I told you, this is called what is virtual height. Now let us see what happens in this case. So for that, let us assume that this ionosphere is layered in nature. That means the density over a very small height does not vary. So there will be a small height with a particular density, then above that there will be another small height with a particular density. So these heights, let us call these heights as from the earth surface, let us go up to a height of Z1. It is in the Z direction, so altitude of Z1. So from Z1 up to Z2, the density remains constant. So if the density remains constant in that layer of the ionosphere, dialectic constant will be epsilon r Z1. From Z2 to Z3, again density remains constant. In that layer, it is epsilon r Z2. So that way it goes up. Now we are sending an electromagnetic wave which is incident onto layer 1 at Z1. Z1 is the first layer. So at Z1 the angle of incidence is psi I. Now if I go to the layer between Z1 and Z2, my epsilon r Z1 will be less than 1. Why it will be less than 1? We have seen an expression for epsilon r which is equal to root over of 1 minus omega square p by omega square. Now 1 minus omega square p by omega square, when omega square is greater than omega square p, in that case this 1 minus omega square p by omega square will be less than 1. If it is less than 1, then its square root will be less than 1. So epsilon r Z1 is going to be less than 1. But below that, below Z1, epsilon r is equal to 1, which is the free space. So 1, then above that it is less than 1. As you go to the next layer, epsilon r Z2, that will be less than epsilon r Z1. The next layer it will be less than the epsilon r z2, and the epsilon r z3 will be less than epsilon r z2, so on. If I divide it into different layers, small layers, infinitesimal layers, epsilon r is equal to 1, epsilon r z1 is less than epsilon r, which means epsilon r is equal to 1 is a denser medium compared to epsilon r z1. Therefore, as you go from epsilon r, which is the atmosphere, into the ionosphere, the ray will bend following the Snell's law. It will bend away from the normal. So that is what is shown here. So it bends away from the normal in the first layer. Then from the first layer to second layer density is less. So again it will bend away from the normal. That will continue till a layer reaches where it reaches the critical frequency, or where the total internal reflection occurs. So from that point it will bend downward. It will come down gradually. So using Snell's law at the boundary of each layer, you can see that sin psi I is equal to sin psi 1 root over of epsilon r z1. That will be equal to sin psi 2 root over of epsilon r z2, and so on for all the layers. Now total reflection, total internal reflection will occur when psi is 90 or pi by 2. So this bending becomes pi by 2. So when it becomes pi by 2, then you have total internal reflection. So for psi n in the nth layer, suppose this occurs, so psi n is equal to pi by 2. So for that we will have sin psi 1 is equal to root over of epsilon r zn. So that is where the total reflection occurs. That is from that point it will come down. So it will be coming back to the earth. So this explains why it comes back to the earth, or why there is a bending of the ray or bending of the beam when we send a beam from the earth to the atmosphere at the proper frequency and proper incident angle. Now if I have constant psi I, then for a constant psi I is incident angle. For a constant psi I, higher density, any higher density will be required for high frequencies if the ray has to come back. So psi I remaining constant, frequency is more, or frequency increases with any for coming back, for bending. If you have a lower frequency, or you have a lower any for a given frequency, then it will not come back. So because this epsilon r decreases with omega, this is a requirement. Then similarly for a given maximum NE, if NE is fixed, maximum NE is fixed, so this will be my NE, this is given, it is fixed, then the maximum value of psi I, that will result in the ray returning back to the earth, will increase with frequency. So so we saw two cases now. Psi I is constant, you require higher NE, you require higher frequency for higher NE, or higher NE for higher frequency. Otherwise NE is constant, we require maximum value of psi I for returning back to the earth with increasing frequency. The relationship between frequency psi I for a given NE max is, we have just seen, sin psi I is equal to root over of epsilon r z1. This is for the ray to bend back to the earth. That is what we have seen. Sin psi I is equal to root over of epsilon r zi. Now from that you can say that sin psi I is equal to 1 minus omega square p by omega square. That we have already seen. Epsilon r is equal to square root of this. So from this we have found out what is this. Now let us put sine square psi I as 1 minus cos square psi I. So if I put that 1 minus cos square psi I, on the right hand side we have 1 minus omega square p is 81 Nemax that I have told you, divided by f square. Now omega square p by omega square is 2 pi f square p by 2 pi square f square p by 2 pi square f square. So 2 pi square cancels out, then f square p is 81 Nemax divided by f square. Now from that you can say that Nemax is equal to, you can easily find out what is Nemax. Take that to the 1 cancels out, minus sign cancels out. So Nemax is equal to f square cos square psi I divided by 81. So Nemax will be f square cos square psi I divided by 81, from which you can get what will be f max corresponding to Nemax. What will be f max? F max will be 81 Nemax divided by cos square psi I. So f max is equal to 81 Nemax by cos square psi I. 1 by cos square is 1 by cos is sec. So this will be root over of 81 Nemax sec square psi I, or f max will be 9 root over of Nemax into sec square psi I. Now let us see one example. Now let us take Nemax is equal to 2 into 10 to the power 10 per meter cube. So number of electrons per meter cube is number of electrons per meter cube is fixed. We have fixed that 2 into 10 per 10 per meter cube. Now suppose the angle of incidence is 60 degree. So psi I is equal to 60 degree. Find out what will the maximum frequency for which the ray will bend back towards the earth, and that is the question. So f max, use this same formula, 81 Nemax is 2 into 10 per 10 divided by cos square psi I. Psi I is 60, so cos 60 is 0.5 or half, so 0.5 square. So take that root over, that will give you 2.5 megahertz. So simple example. Similarly, if I take it as 45 degree instead of 60 degree, so this 2.5 megahertz will be 1.8 megahertz. So calculate that yourself, you can see for different angles. So we have taken 60, 45. Take what will happen if I take 30 degree, or if we take 75 degrees. So find out what is going to happen, what are the frequencies, and from this you can see that clearly you can see this thing. The angle is Nemax is fixed, angle of incidence is decreasing, and frequency, maximum frequency is decreasing. That you can easily see. 60 it is 2.5 megahertz, 45 it is 1.5 megahertz. Similarly, if you change Nemax, keep instead of this Nemax is equal to this what we have taken, instead of that fix psi I at 60 degree or 45 degree and change Nemax, find out what will be f max. You can again see the relationship that we just discussed, that for constant psi I, higher Ne is required, you will require higher Ne for higher frequencies. Similarly, for a given Ne, this one we saw, for a given Ne you require maximum value of psi I, that results in a ray return to the earth. That will increase with frequency, that we have seen. You increase the frequency, psi I keeps on increasing. So that part, and this part we have seen in these two examples. Then our critical frequency for a given Nemax is that frequency for which epsilon r is equal to 0. This is the definition. What definition of critical frequency? Critical frequency for a given Nemax is that frequency for which epsilon r is equal to 0. Now if you put that those values in Fc, so Fc will be 9 root over of Nemax. So this expression we have already seen, just repeated this one. So otherwise it has no utility. Okay, So now let us see what is called a maximum usable frequency. So that is something that we will see. That comes from this law, secant law or Martin's law. This says that if we use the expression for any max in critical frequency and solve for a frequency f, then we will get f is equal to 9 root over of any max into sec psi I. This we have already seen. In the previous case we have seen when we solved for f was root over of 81 any max divided by cos square psi I. So 81 root over is 9, any max root over is any max root over, 1 upon cos square psi I root over is sec psi I. So f is equal to this. Now 9 root over of any max is fc. So f is equal to fc into sec psi I. This is called the secant law. F is equal to sc into sec psi I. This is called secant law or Martin's law. From this we find a frequency which is called the maximum usable frequency or MUF. Now when this sec I will have its maximum value, that is the angle of incidence on the ionosphere for which sec I has maximum value, the frequency is called maximum usable frequency. The frequency for which sec psi I gets the maximum value is called the maximum usable frequency. Right? So this maximum usable frequency gives us also the maximum incident angle on the ionosphere. So these are the two things that we get from secant law. Now this maximum usable frequency, you can see, is on the left side. On the right side or on the x-axis, on the y-axis we have maximum usable frequency. On the y-axis we have time. So 0 to sunrise to sunset, then to midnight. So 0 to 24 hours is shown here. In this you can see that before sunrise in all the layers from 500 kilometers to 3500 kilometers, in every layer it is gradually decreasing and coming to a dip at around 6 o'clock. This is almost throughout world. So maximum usable frequency is lower. Then it peaks at the noon. So when it is 12 o'clock, so it peaks. The maximum usable frequency in different layers, it peaks. After that gradually it decreases. So gradually it diminishes or decreases or attenuates as we go towards the sunset. What can be the reason for this? In the noon there will be maximum density, which means any max is maximum. Therefore we naturally expect that maximum usable frequency will be maximum in the noon. In the afternoon or in the morning, this will be minimum. So those who are dying down. Right. So that is what is shown here. And the typical value for maximum usable frequency is less than 40 megahertz. It can go below 20 megahertz during low solar activity periods. Optimum usable frequency, like maximum usable frequency, there is something also called a optimum usable frequency, which we use to be 50% to 80% of maximum usable frequency. Why this is done? The reason is if always we use the maximum usable frequency depending on solar activities, season, etc. You are suppose maximum usable frequency is 40 megahertz and we are using 40 megahertz. Because of solar activity it drops down to 30 megahertz. We do not know that and it has dropped down to 30 megahertz. So in that case we will be in fixed because that is not useful. So therefore usually we use in the range of 50% to 80% in the summer region, summer season it will be 80%. In the winter season we can go down to 50%. And this is particularly correct. This assumption and this figure is particularly correct if we have a horizontally stratified media or horizontally stratified ionosphere. So stratification or layers that I told you. So that is horizontal to the earth surface. In that case this is true. Otherwise we require other things which are not in the scope of your course right now. So I hope you have understood up to this. Now let me see or let us see what happens or how the communication occurs using ionospheric radio propagation. As I told you, we are initially first we will consider the earth surface to be a flat surface. Instead of taking its curvature into account, let us consider it to be flat. Now if it is flat, we are sending from the left end, we are sending a electromagnetic wave to the atmosphere with correct frequency and correct psi I or the correct angle of incidence. It will go to the atmosphere, bend back and come back and hit the earth. This is called single hop. So from one point it goes to the other point. It hops from one point, transmitting point, to the receiving point. So this is called single hop. You can have multiple hop, but in this, when we have a flat earth consideration, the flatness is for a limited range. If you increase the range, then this flatness will not be there. It becomes curvature. So the second hop will not meet the earth. It will go beyond the earth. It will go tangentially or out of the earth surface. So if we consider a flat earth, that is what is going to cause problem for multiple hops. You can have a single hop. So this is called a single hop model. Now in this model, you can see that the psi I that can be related to this distance d, capital D and h dash. Now you can see this figure, we can divide it into two sides, two symmetric parts, in the left part and on the right part. This h dash is perpendicular to D, and since it is symmetric, so where this h dash touches the earth surface, that is the D by 2 point. So if the total distance is D, this is the height h dash is measured from the center of the hopping point, which is D by 2. Then from that to the hopping point, it is again D by 2. So h dash and D by 2, we have a triangle. Now you can see that we have got a right angle triangle. In this right angle triangle, the angle psi I is given to us. So from that we can find out what is tan psi I. Psi I is the incident angle. So since it is the incident angle, at the point of reflection the angle also will be psi I with the normal or with the h dash. So that will be psi I. Therefore tan psi I will be d by 2 divided by h dash, which will be d by 2 h dash, because you know tan is equal to p by b, perpendicular by base. Now that angle psi I, base is h dash, perpendicular is d by 2. So from that we find out tan psi I is equal to d by 2 h dash. From that we can easily find out what will be my skip distance. D is called the skip distance. D you can find out D, or the distance, single hop distance, hopping distance, not skip distance, is the hopping distance. So hopping distance you can always find out. D is equal to 2 h dash and tan psi I, depending on the angle of incident. Now the angle of incident can be such that this will not come back, this will go back, go away. If that is such that, so then the D is called the skip distance. For D, the D where this one occurs, psi is such that it is not coming back, that D is called the skip distance. So this is for the flat earth model. Then we can also have the a curved earth model or regular earth model where we have got multiple hops is possible because of the earth's curvature. When we consider the curvature of the earth, you can see that there is possibility of multiple hops. So from transmitting point it goes to the ionosphere, comes back, then gets reflected from earth surface, go to the ionosphere, comes back, gets reflected to the ionosphere, comes back towards earth. It may meet, the third one may meet or may not meet the earth. It may go away tangential. So third, fourth, which number of hop will go away tangentially we don't know, but we can have multiple hops. In this case, if that is possible, then d is equal to 2 times root over of 2 re dash h dash. H dash, you know, I have told you, h dash is the virtual height. So I am not worried about h dash. What is re dash? Re dash is effective radius of the earth. What is effective radius of the earth? You know, earth is not a perfect sphere. Therefore, what we assume earth to be a sphere. So if we assume earth to be a sphere, the radius of that sphere is the effective radius of the earth. So r dash is the effective radius of the earth. Now in this multi-hop, this allows for very long range communication. Single hop has limited range, but multi-hop, since you are hopping more than once, so you can go for a very long range communication. In effect, you can go for transcontinental communication using multi-hop. So using a simple flat earth model, we have seen this virtual height, incident angle and skip distance are related by this expression tan psi I is equal to d by 2 h dash, but which implies that the wave is launched well above the horizon. If wave is launched well above the horizon, then we get this single hop model is correct. But if we consider spherical earth model and use it, then the wave is to be launched on the horizon, and in the wave on the horizon, then d will be equal to 2 root over of 2 r dash s dash. This derivation we will see in a minute, in 2-3 slides from now. We will see that derivation. Give me a moment, let me take some water. Now let us come back to ionospheric layer and consider the virtual height. Approximately what is the virtual height? Let us try to understand what happens to the virtual height. Coming back to ionosphere. Coming back to the ionospheric layer. As I told you, we have different layers: D layer, E layer, F layer, etc. So E layer is at a range of 110 kilometers. So below that is D layer. Above that, from 300 kilometers, that is in the night, we have got F layer. In the day, we have got 200 to 250 as F1 layer, 250 to 400 as the F2 layer. In the night, F1 and F2 merge together, and we get the F layer at 300 kilometers. So try to remember this table. A thumb rule for maximum incident angle, considering this layer, is thumb rule. So maximum incident angle, it has to be below 74 degrees. Now a maximum usable frequency, if I consider this as the maximum incident angle is 74 degree, maximum usable frequency, we have seen the expression Fc into sec of psi I. Psi I is 74, so Fc sec 74 degree, that will be 3.6 Fc. So maximum usable frequency will be about 3.6 times Fc, which is the cutoff frequency or the plasma frequency or critical frequency. So anything you can say. Now let us see one example. Nemax is 10 to the power 12 per meter cube. So for that we are considering Fc is equal to 9 megahertz. Approximately 9 megahertz is my Fc. If Fc is 9 megahertz, then maximum usable frequency is 3.6 into 9 megahertz. So that will give me about 32.4 megahertz. And the maximum skip distance for reflection from the F2 layer. Suppose we are considering the F2 layer, highest layer, from that it is coming back. F2 layer is at a distance of 300 kilometers. So from that we are going to find out the maximum skip distance. So that will be, how do you find out maximum skip distance? Dmax will be, we have seen in the previous slide, Dmax is equal to approximately 2 times root over of 2 RE dash H dash. So it is 2 times root over of 2 RE dash. Effective radius of the earth is 8500 into 10 to the power 3 meters. 8500 kilometers, or 8500 into 10 to the power 3 meters. That into H dash is 300 kilometers, so 300 into 10 to the power 3. So root over will give me 10 to the power 3 into 10 to the power 3, root over is 10 to the power 3. So from that we get kilometer, and 2 into 8500 into 300 root over into 2 is equal to 4516. So Dmax is equal to 4516 kilometers. So this is the skip distance. So if you start from one point at a distance of 4, so the angle between the incident ray and the tangent is delta. That is called the launch angle. R by 2 is the distance from the launching point up to the reflection point. So launch angle delta, you can, from this you can easily find out what is launch angle delta. Delta will be phi minus 90 degree. Why phi minus 90 degree? Because you draw a perpendicular tangent at the point where it is touching, where RE is touching the surface, then that is perpendicular to RE. Now the surface over a small range, surface can be flat. So this is 90 degree, phi is equal to 90 degree cos delta. Therefore delta is equal to phi minus 90 degree. That also you can say that that is in terms of the larger triangle, you can say delta is equal to 90 degree minus theta minus psi I. The total theta plus psi I plus the whole angle is 180 degree. From that you can say delta is equal to 90 degree minus theta minus psi I. From where 90 degree comes? Because it is 100, delta will be 180 minus psi I minus theta minus 90 degree. 90 degree is the angle because of the tangent drawn at the surface of the earth. So from that you get 90 degree. 180 minus 90 gives you 90. So 90 minus theta minus psi I. This is a relation which is the three angles of the triangle, they add up to give you 180 degrees. So from that we get this relationship. So launch angle delta is equal to 90 degree minus theta minus psi I, which is equal to psi minus 90 degree. Now you know the law of sines. From law of sines you can say that RE divided by psi I is equal to H dash plus RE dash into cos theta, which is the part from the center of earth to the top of the earth, or surface of the earth in the direction of the virtual height. That will be cos theta, RE cos theta. Why it will be RE cos theta? From the RE dash point where it is at to the point where H dash touches the earth, that portion if we take as a line, which is perpendicular to this line H line, and then this triangle is a right angle triangle. In that right angle triangle, you will get cos theta is equal to r dash by this distance. So from that distance is equal to r dash cos theta. So from that is what you get. So r dash cos theta plus h dash divided by sine of phi. So sine r dash cos theta plus h dash divided by sine of phi is equal to r dash divided by sine of psi I. Now phi, we have seen phi is equal to phi minus 90 is equal to 90 minus theta minus psi I. So phi is equal to 180 minus theta minus psi I. So sine of phi will be sine of 180 minus theta minus psi I. That will give you sine of theta plus psi I, which is in the form of sine A plus B, sine A cos B cos A sine B. So put those values and do some simple algebraic manipulations that will give you this relationship. So from law of sines we get 1 cross h dash by r dash minus cos theta by sin theta, which will be equal to 1 upon tan psi I. Now what will be theta? Theta you can easily find out. This we have used earlier in the flat earth case. This theta you can easily find out what is theta from this triangle. Now theta is very small. Actual theta is a small angle. I am showing you here a very expanded version, but if it is very small, when theta is very small, you know, theta will be d by 2 divided by r dash. D by 2 divided by r dash, that will be theta, because that will be tan theta. Tan theta is approximately theta for theta very small. So that gives you this. Theta is equal to d by 2 divided by r dash. So from that you get theta is equal to d by 2 r dash. So from this, this actually gave you, we used this value earlier for the flat earth model. What is capital R in this case, or r by 2? That capital R is a great circle path via the reflection point in the top. That reflection via the reflection point you get capital R. Therefore, capital R will be 2 r dash sin theta by sin psi I. This also comes from this law of cosine, law of sines. So this part we have seen. Now on the final part is the modification to Friis equation. When we are using ionospheric propagation in the ionosphere, there will be some attenuation. Otherwise, you know, from Friis equation is usually PR is equal to, PR is received power is equal to transmitted power into gain of the transmitting antenna GT into gain of the receiving antenna. So GR that remains as it is, divided by 4 pi r upon lambda whole square. So that part remains as it is, into Lx into La. Now what are these things? So Lx is equal to L pole plus L reflect minus G ionos, which is L polarized value, reflection loss if there are multiple hops. L polarized is polarization loss due to Faraday rotation and Earth reflections. This we'll see later what is Faraday rotation. G iono is gain due to focusing of the curvature of the ionosphere. So that will be, because the moment you have a curvature, it is like a parabolic dish. A parabolic dish, you know, a parabola or parabolic mirror, you must have straight curved mirrors, plane mirror and curved mirror, a flat mirror or curved mirror. So there you consider a parabola that reflects. Here it is a reflecting region, and that will reflect because of this. So the gain due to this reflection. Then La is absorption loss. Absorption loss is absorption in the ionospheric layers. So since there are electrons and other gases are present, so they will absorb some amount of electromagnetic energy, so that the loss due to that absorption is absorption loss. R, as I have told you, this is the great circle path via the virtual reflection point. So from that point this circular path. So these are the points that I wanted to discuss today. So we'll stop here for today. We have almost covered most of the important parts of ionospheric propagation that usually comes in your NET examination or GATE examination. These are the parts that you see.